So today we're going to start Chapter 7, Section 2, and we're going to talk about different properties of parallelograms. So the first slide has the definition of a parallelogram. And a parallelogram is going to be a quadrilateral with two pairs of parallel sides. When you want to write out the name of a parallelogram, you don't need to sit here and write the word parallelogram each time. You can just put this little picture of a parallelogram in front of the four vertices. So if I wanted to name it, again, just draw like a slanty rectangle, and then you put A, B, C, D. Make sure you go in order. So pick a starting point. So since I picked A, I went in alphabetical order. I went to the B, then I went to the C, then to the D. So make sure you pick a starting point and then go straight around the edges. I could have also gone backwards. I could have started at A and then went to the D and then went to the C and then went to the B. It doesn't matter where you start, just go around the edges. Now, also notice on this picture that these arrows on the sides, these are parallel indicators. So it's telling me that AB is parallel to CD, which is that statement. And then it also, more parallel marks. And notice it's got two of them. So BC is parallel to DA. So by definition, a parallelogram is a quadrilateral with two pairs of parallel sides. Yes? Okay, so now let's go on and learn two theorems about parallelograms. These are still properties, but now they're officially presented as a theorem. So the first one, again, the number is not important. If you want to memorize the name is the parallelogram opposite sides theorem. And what this theorem states that is if a quadrilateral is a parallelogram, then its opposite sides are congruent. So we could go ahead and add to our picture now. Not only are sides A, B, and C, D parallel, but they are also congruent. And then the same thing here, BC is parallel to DA, and it's also congruent. And that's what the statement over here for the conclusion says. The second theorem on here is the parallelogram opposite angles theorem. Same idea. Opposite angles are congruent if it's a parallelogram. So here, A is going to be congruent to C, and then B will be congruent to D. These are opposite angles. And that's what's stated here in the conclusion. Our next two theorems, the first one talks about the consecutive angles theorem. So this is stating that if a quadrilateral is a parallelogram, then its consecutive angles are supplements. So again, if you talk about consecutive integers, those are numbers in order. Same idea here, if you pick angles in order. So for example, if you start at A, and then the next angle you could come to would be B. If you add these two together, they're going to add up to be 180. They're supplements. If you recall back from your prior knowledge that because these lines are parallel, and this is the transversal, these are consecutive interior angles. Or what was the other word we called them? Same side interior angles. That's how this theorem comes about. And then if you started at B and then add that to C, that's also equal to 180. Or if you started at C and then the next one you come to is D, that's also supplements. And then lastly, if you do A and D together, they're also supplements. Because we have our parallel lines here, and then this is the transversal, making them same side interior angles, which are supplements. So this quadrilateral chapter is going to bring back a lot of the stuff we did in the first semester. If a quadrilateral is a parallelogram, then its diagonals bisect each other. So the diagonals are the lines inside. So this would tell me that BZ is congruent to DZ and that AZ is congruent to CZ. The diagonals are bisected. So now we're just going to do some examples using these theorems and the definition that we just learned.
Would all of the segments of the diagonal ever all be congruent to each other, or is there always two incongruent to incongruent?
In just a parallelogram, they're just the same, they're congruent to each other. In a rectangle, the diagonals are going to be congruent, and then all four little pieces would be congruent. But right now, in the parallelogram, they're separate. So what's going to happen is, as we move through the chapter, we're going to get each different type of quadrilateral is going to add more properties to the parallelogram. So the square is going to have, well, for example, the rectangle is going to have all the properties of a parallelogram, and then we're going to add a few things. And one of the things we'll add is that their diagonals are congruent, and another thing we're going to add is that it has 4 right angles. So we're going to add more specifics to each type of quadrilateral as we go through. Pretty good on this slide? Let's try the next one. Okay, so the first one's not too bad. It's just asking us to name all pairs of parallel lines. So by definition, all right, first of all, before we even start answering these questions, you need to be given that this is ABCD is a parallelogram. If they don't tell me that this is a parallelogram, I can't assume anything about this figure. So you would have needed to be told that this is a parallelogram, and since it is, then I know that opposite sides are parallel. So I could state that AB is parallel to DC, and that BC is also parallel to AD. These are the parallel sides. Now, number 2 is going to be a lot of congruent angles here because they actually drew in the diagonals. So let's go ahead and get ready to name a bunch of different congruent angle pairs. So first we're going to do the obvious using the theorem that we just learned. So we're going to say that this angle over here is congruent to this angle over here, because we just learned the theorem that if a quadrilateral is a parallelogram, opposite angles are congruent. Now, because they drew in those diagonals, I can't just say A is congruent to C. I need to name these angles with 3 letters. So I am going to name this as BAD, this one. Angle BAD is congruent to angle DCB. Now I could have gone in the other order. I could have also called this DAB congruent to BCD, but just notice the A and the C are in the middle. These both mean the same angles. Then the other pair of opposite angles that I have here is this one over here and this one over here. Again, I need to name it with 3 letters. So I'm going to name this angle ABC is congruent to angle CDA. And both of these are the opposite angles, and I would use the opposite angles theorem, because I knew opposite angles are congruent when it's a parallelogram. All right, next, because I have parallel sides, because this side is parallel to this side, I can use my my diagonal, and it becomes a transversal, making alternate interior congruent angles. So here, I'll just put it with one mark. One is congruent to this one, but then this one over here is congruent over here because they're alternate interior angles. And again, I'm using the parallel sides, and then I use the transversals. I know my picture is getting really busy. All right, so let me go ahead and name these angles. So this black one right here, along with this one is angle, let's see which one we're gonna name this one as. We can say this one is CAD is congruent to BCA. And then I have the green one that I did, and that one's going to be the BAC is congruent to DCA. And these are alternate interior. And then I have the other ones. I can do the same thing over here. I've got this one congruent to this one. And then 1, 2, oh, I should use a different color here. Let's do yellow. 1, 2, and 1, 2. So these are going to be named as CBD. Angle CBD is congruent to ADB. And then the other one in yellow, this could be ABD, is congruent to CDB. And these are all alternate interior pairs. Then surrounding angle E, I've got vertical angle pairs. So we're really reaching back to that first semester to find all of these congruent angle pairs. So let's see, we've got this one, 2, 3, 4, 1, 2, 3, 4. Those are congruent to each other. And again, these are all vertical angles. So I could call this angle BEC is congruent to angle AED. And then I have the other vertical angles on the other side. 1, 2, 3, 4, 1, 2, 3, 4. So I could call this AEB is congruent to CED.
Miss Chloe,
Yes.
so these are all still for number 2?
Yep.
Okay.
Now for number 3, I'm going to redraw the picture because I got way too many markings in this picture. Yes.
How come for the alternate interior angles, you did it CAD? How come you do EAD?
You could use E. I just went all the way to the corner vertice. You could use the E on those. All right, now we're going to do part 3. And I'm going to redraw the parallelogram. So A, B, C, D with the diagonals here. And this is an E. So it wants me now to name all the congruent segments. So I know opposite sides are congruent. So I could say here that AB is congruent to CD. I know that this pair of opposite sides are congruent. So I could say that BC is congruent to AD. And now because they've also drawn in the diagonals, I know diagonals bisect each other. So these are just these two are the opposite congruent sides. And now I'm going to use the diagonals. And because the diagonals have been bisected, I know that BE is congruent to ED. So this congruent to this. And then AE, 1, 2, 3, 4, 1, 2, 3, 4, is congruent to EC. So a lot of congruent parts here because they drew in the diagonals and because they told me this was a parallelogram.
On a test, would you ever ask us to list out the angles like that?
I probably would give you something that didn't have diagonals. I don't think I'd ask you to list that many. It's way too many. And then it would get too confusing for me to grade anyways, because depending on how you named your angle, like for example, when I named this angle, you could have either called it BEA, or you could have gone this way and called it AEB. So because something like this on a test would create a major nightmare for me, I probably would not ask you to name all of those angle pairs.
But it might ask like which of these angles is congruent to the angle list, and it'll give you an angle between.
Exactly. Yeah. Everybody good on example 1? All right. Example 2 is not as bad, but it does have 3 parts. Let's try example 2. So it's telling us that these are a parallelogram. Now, notice C doesn't have letters. Let me just go ahead and add some letters. R, S, T, U. And I'm also, number 1, or part A is missing a little a. So let's go ahead and find the value of all these variables. So the first one's pretty easy because there's really no expressions to solve for. I'm going to use the theorems I just learned. And I know that opposite sides are congruent. So if this side is 9, then little b is 9. Same thing here. If this side is 6, then the side across from it or opposite is also 6. And same thing with the opposite angles. So if this angle is 80, then angle X is also 80. Now, in order to find y, though, I'm going to use the consecutive interior angles. So I know that 80 and y, these are going to be supplements. So what I could do here is 80 plus y equals 180. Subtract 80, and y equals 100. So generally, if you're not sure what letter is representing either a side or an angle, usually the variable will have a little degree symbol. Same thing with the numbers. If you're not sure what it's referring to, the angles have the degree symbol. The outside side lengths will just have a number. Sometimes they'll even have a unit, like inches or centimeters. Okay, but generally the side length numbers are written outside of the picture. Let's try part B. So again, to find the measure or what A equals, again, opposite sides are congruent. So A is 12. B is on the diagonal. I know diagonals are bisected, so I know B is going to be 9 because these are congruent. And now here's where I'm pulling in my parallel sides and my transversal. So if I use this diagonal as being my transversal and using these parallel sides, making y and 45 alternate interior angles. So little y is 45. And x, now x is referring to this whole angle here. So x, because notice it has the degree symbol, I know that this angle x that they're asking me to find is going to be supplement to this whole thing here. All right, so this angle along with this angle, these are supplements. So I'm going to do 45 plus 35 plus x equals 180. Yes. Yes. 45 plus 35 is 80. Subtract 80, and angle x is 100 degrees. Yes.
So are they saying x is the whole angle, or is it just the part, the diagonal?
Well, because it has a degree symbol, I know this one's kind of misleading of what it's pointing to. So because x has a degree, it's pointing to the whole angle here. So this whole little corner. Now, if it didn't have the degree symbol on the variable here, then I would have thought it was pointing to the diagonal.
No, not the diagonal itself, but the smaller angle created by the diagonal.
We don't have enough information to figure out that smaller angle individually. So that's why it's pointing to the whole thing.
Would it be more clear on the video?
It'll be more clear of what it's pointing to. But if you're not sure, you can always ask. But it'll be a little bit more clear. All right, let's try part C. So here, all I'm using is the theorem that states that opposite sides are congruent. So 8 is congruent to 4x. So I'll go ahead and set up that equation. Divide by 4, and x equals 2. And then for the other one, 3y plus 4 is congruent to 13. Solve for y by subtracting 4. Divide by 3. And y equals 3. So for example 3, it wants us to find the perimeter of parallelogram PINE. Notice a picture is not provided, so I'm going to go ahead and give myself a sketch. So I'm going to draw a parallelogram. I'm going to label it PINE. It told me the length of PI is 12 and the length of IN is 8. So I'm going to go ahead and use the theorem that I just learned, that opposite sides are congruent. So if this side is 12, I know this side is 12. And if this one's 8, then this one's 8. To find the perimeter of any figure, you're going to go back and you're going to add up the sides. So I'm going to add 8 plus 8 plus 12 plus 12, giving me a grand total of 40. So the perimeter of parallelogram PINE is 40. Notice no units were given, If it were in inches, you would say inches. We could just say units. So I'm going to set up my 2-column proof here. Statements, reasons. I'm going to start by stating the given that A, B, C, D, and G, D, E, F are parallelograms. And that was given to me. Now what I can do is think back to the theorems that I just learned, because my goal is to show that this is congruent to this. So I'm trying to get B congruent to F. So first thing I'm going to do is talk about the opposite angles in this green parallelogram. And I could state that angle B is congruent to angle CDA. And that reason, I could either state the name of that theorem. I could either label this as the parallelogram. And you could draw the little picture. Opposite angles theorem. You can either just state that, or you could state what it says. So, or you could tell me that if a quadrilateral is a parallelogram, then its opposite angles are congruent. So you can either restate what that theorem says or give me the name. Now, since I've already got all of those words written, I'm also going to say the same thing about this little parallelogram. And I'm going to also, in that same statement, say that angle F is congruent to angle EDG. So far, I've labeled that my goal was to get these two congruent, but I've established in my proof that this is congruent to this, and that this is congruent to this. So now what I need to do is show some kind of relationship of these two. And if you reach back to the beginning of the year, these are actually called vertical angles. So I'm going to establish that angle CDA is congruent to angle EDG, and the reason is the vertical angles congruence theorem. And remember, I abbreviated that as VAT. So this is the vertical angles congruence theorem. Again, you can just put VAT. Now that I've established that in step 2 that B is equal to CD and F is equal to EDG, now I can do a substitution. So now I could just take and substitute and say that angle B is congruent to angle F, and that's what I was trying to prove in that substitution. And there's your first proof of chapter 7. So it says 3 vertices of parallelogram WXYZ are W, which is -1, -3, X, which is -3, 2, and Z, which is 4, -4. It wants me to find that 4th vertice, which is Y. So my first step is going to be graphing these vertices. So I'm going to go ahead and put a picture in here. Let me see if I can add a picture to my slide. So step 1, graph vertices W, X, and Z, which is what was given to me. So W is over here at -1, -3. That's W. And then I'm going to graph y, which is at -3, +2, which is here. That's x. And then I'm going to graph z at 4, -4. And that's z. It wants me to find the fourth coordinate. Now, the way that we have to officially do this is, remember, opposite sides are parallel. So what I'm going to do is, I remember that parallel lines have the same slope. So I am going to find the slope of wx. So step 2, find the slope of wx. So the slope, and again I'm going to use my ordered pairs, which were up here, the -1, -3, and the -3, 2. So I'm going to do 2 minus -3 divided by -3 minus -1, and I get 5 over -2. So this is my slope. So now what I'm going to do to figure out where that fourth coordinate's going to be, I'm going to take that slope. So I'm going to start at the ordered pair for z, because I need to make the connection and I need to find where that other point's going to be. I need to find where yz is. So I'm going to start at point z, which is 4, -4. And then I'm going to use the slope, the rise and the run. So I'm going to rise from that point, -5 over 2. So if I go over here and I go up 5. All right, so from here, I'm going to rise 5 and run 2. So 1, 2, 3, 4, 5, and then I'm going to run 2. And that's going to be the coordinate for point y. So you're going to see that y is going to be the ordered pair 2, 1. Because now if you connect this side, you can see that it forms a parallelogram. So y is the ordered pair 2, 1. Now, one way that you can confirm this is you can also now, just to double check it, you're going to find the slopes of xy and wz to make sure that they're parallel, to make sure you get the same slope. So this is a way that you could check to make sure that everything has the same slope and like opposite sides have the same slope, making them parallel. So the slope of xy is going to be 1 minus 2 over 2 minus -3. And this gives me -1/5. And then if I find the slope of wz, that's going to be -4 minus -3 over 4 minus -1, which gives me -1 over 5. Because these are the same slope, I know that the sides are parallel. So I did find the correct coordinate. So the coordinate for y, let me fix that, is the ordered pair 2, 1. So that is your answer. You know, you could probably try to guess where it is and then just confirm that the slopes are the same for all the sides. But this is the official algebraic way to find the missing coordinate. Now, in the homework tonight, I took off these problems where you have to find the missing coordinate. I'm going to add it to tomorrow night's homework. But tonight is the assignment that's up there, and it's due tomorrow morning, 8 a.m. So we're actually going to spend 2 days on this. Tomorrow I'll go over anything in the homework that you're confused on. I'm going to try to get in some more proof practice, because in section 7.3, we're now going to have to prove that something's a parallelogram. So we're going to take the converse of all the theorems we learned today. So again, lots of proofs for chapter 7. So that is it for the notes on 7.2.